It's a Spotify podcast.
You pushed me down, thought I'd stay on the ground, counting me.
Hey everyone, and welcome to another Rabbit Holes Deep Dive. Tonight we're talking about the machine that ate the grid. When artificial intelligence became an energy story. I know this is on a lot of people's minds, so let's dig in. Imagine being asked to build a city. Not the houses, not the roads, not the schools, just its electrical appetite. 10 gigawatts. Enough generating capacity to rival the demand of millions of homes. Now imagine that almost all of that electricity is being planned for one purpose: computing. In southern Ohio, the U.S. Department of Energy announced a partnership in March of 2026 built around an extraordinary pairing. Plans for a 10 gigawatt data center development alongside 10 gigawatts of new power generated. At least 9.2 gigawatts of that proposed generation would come from natural gas. Think about that number for a moment. We have spent years talking about artificial intelligence as though it existed somewhere intangible. Algorithms, models, tokens, chatbots, the cloud. And AI may be helping change what the grind is for. Most of us interact with artificial intelligence. The experience feels almost, wait a minute, did I? Like that. The machine that ate the grid. When artificial intelligence becomes an energy story. Imagine being asked to build a city, not houses, not roads, not schools, just its electrical appetite. 10 gigawatts, enough generating capacity to rival demand of millions of homes. Now imagine that almost all of that electricity is being planned for one purpose: computing in southern Ohio. The U.S. Department of Energy announced a partnership in March of 2026 built around an extraordinary pairing. Plans for a 10 gigawatt data center. Development alongside 10 gigawatts of new power generation. At least 9.2 gigawatts of that proposed generation would come from natural gas. Think about that number for just a moment. We have spent years talking about artificial intelligence as though it existed somewhere intangible. Algorithms, models, tokens, chatbots, the cloud. But there is nothing particularly cloudy about a gas turbine, or a transmission line, or a transformer, or a cooling system, or a power plant. And that leads to a question that may turn out to be much bigger than AI itself. What happens when a digital revolution starts demanding industrial scale physical resources? Because something unusual is happening to the world's electricity system. And AI may be helping change what the grid is for. The invisible factory. When most of us interact with artificial intelligence, the experience feels almost weightless. You type a question, a response appears. Maybe it takes 3 seconds. There is no smoke, no machinery, no visible fuel, no obvious infrastructure, but somewhere, something very physical just happened. Electrical power flowed through transformers and switchgear into building containing thousands or potentially tens of thousands of specialized processors. Those processors performed enormous numbers of mathematical operations. They produced heat. Cool equipment removed that heat. Networking equipment moved information between machines. Backup systems waited in case the grid failed. And all of it happened so quickly that from your perspective, it looked like words appearing on glass. That illusion may be one of the most important things to understand about AI revolution, because the internet trained us to think of computation as nearly immaterial. But computation has always been physical. AI is simply making that fact much harder to ignore. Lawrence Berkeley National Laboratory estimated that American data centers consume about 176 terawatt hours of electricity in 2023, representing approximately 4.4% of the total U.S. electricity consumption. By 2028, its earlier analysis estimated that data centers could consume somewhere between 6.7 and 12% of the U.S. electricity. The Department of Energy's subsequent updated outlook extends the forecast to 2030. Its central estimate, about 11.8% of the total U.S. electricity use, its scenario range stretches from approximately 9.5% to 15.3%. Those numbers are projections. They are not destiny. And that distinction matters. Some proposed data centers will never be constructed. AI hardware could become more efficient. Algorithms could require less computation. Investment could slow. Companies may discover that some AI applications do not generate enough economic value to justify their energy cost. But even the uncertainty tells us something. Grid planners are now seriously considering a future in which data centers consume something on the order of a tenth or potentially more of all electricity used in the United States. That is not merely a technology story. It is an infrastructure story. And infrastructure changes. Civilizations in ways software alone cannot. The number behind the boom. Follow the money and the scale becomes clearer. According to the International Energy Agency, capital spending by just 5 major technology companies exceeded $400 billion in 2025. The IEA expects that spending to increase another 75% in 2026. The agency points out something remarkable. Capital expenditure by those 5 technology companies is now larger than global investment in oil and natural gas production. Read that again. 5 technology companies, more capital spending than the world invests in producing oil and natural gas. Of course, those aren't directly comparable industries, and not every dollar of technology company capital spending goes into AI infrastructure. But the comparison reveals the magnitude or what is happening. AI is no longer merely software investment cycle. It is becoming one of the largest infrastructure investment cycles on Earth. And infrastructure has consequences. You need land, concrete, steel, copper, transformers, transmission lines, cooling equipment, semiconductors, backup generation, water in some design, and above all, electricity, which creates a strange inversion. For decades, computing became more powerful while disappearing from view. Mainframes became desktops. Desktops became laptops. Laptops became phones. Computing seemed to become smaller, lighter, more efficient, more invisible. AI is pushing in opposite directions. The interface may fit in your pocket. The infrastructure behind it can consume the power of a city. The grid wasn't waiting for this. To understand why this matters, we need to understand what happened before AI arrived. For much of the previous 2 decades, American electricity demand was relatively flat. Utilities still built infrastructure, power plants retired and opened. Renewables expanded dramatically. Vehicles began electrifying. But the basic planning environment was relatively familiar. Then several things began happening at once. Manufacturing started returning to parts of the United States. Electric vehicles expanded. Building electrification increased. Semiconductor manufacturing grew. And data centers exploded. The Department of Energy's 2026 draft National Transmission Needs Study now explicitly identifies data centers, domestic manufacturing, and other large industrial loads as drivers creating new pressure for transmission infrastructure. That means something fundamental has to change. The question facing electricity planners is no longer simply how do we replace aging generations. It is increasingly how quickly can we build enough electricity infrastructure for loads that may arrive faster than traditional infrastructure can be constructed. A data center can potentially be developed much faster than a major transmission line. A gas turbine can face equipment constraints. A nuclear plant can take years. A transmission project can become entangled in permitting, land acquisition, environmental review, and local opposition. Transformers themselves can become bottlenecks. And the AI industry has another problem. It does not merely want electricity. It wants electricity soon. That difference matters enormously because an AI arms race waiting 5 years for a grid connection may feel less like a delay and more like losing. So companies and governments are looking for shortcuts, dedicated generation, on-site generation, microgrids, existing industrial sites, federal land, natural gas, nuclear power, storage, flexible computing, anything that reduces what the industry increasingly calls time to power. And once time to power becomes a competitive technology metric, energy policy and AI policy begin to merge. The gigawatt clue. That brings us back to Ohio. The Department of Energy says a public-private partnership involving SoftBank and other participants plans to redevelop federal land around the Portsmouth site. The proposal connects 2 enormous numbers: 10 gigawatts of data center development, 10 gigawatts of new power generation. At least 9.2 gigawatts of the planned generation would be natural gas. The government argues that excess generation and transmission capacity would also be available to the surrounding grid and says the arrangement is designed so that the development does not impose costs on American families. Whether those promises survive the realities of construction, regulation, and electricity markets will need to be measured rather than assumed. But the project architecture is revealing instead of asking, where can we find electricity for the data center? The model increasingly becomes, what if we build the electricity system and the data center together? And Ohio isn't the only example. In July of 2026, the National Nuclear Security Administration selected an amendment to enter negotiations for another project at the Savannah River site in South Carolina. The concept pairs AI data center of up to 1 gigawatt with dedicated on-site electricity generation. Once again, compute plus generation, data center plus power plant, digital infrastructure plus energy infrastructure. The boundaries are disappearing, and that raises a deeper possibility. Perhaps the defining companies of the AI era won't merely be software companies. They may be increasingly resemble industrial conglomerates, companies whose competitive advantages include not just models and chips, but electricity contracts, generation, cooling, land, transmission, access, construction, and the ability to secure enormous quantities of power before their competitors can. The complication. At this point, there is easily a story to tell. AI is consuming enormous amounts of electricity. Therefore, AI will overwhelm the grid. But there is a problem with that story. We don't actually know, and pretending we do turns a fascinating investigation into a simplistic one. The Electric Power Research Institute estimates that AI workloads currently account for roughly 15 to 25% of data center electricity consumption. That share is rising. But ordinary cloud computing, storage, streaming, search, and other digital services also consume enormous amounts of electricity. So when electricity demand from one data center rises, we cannot automatically attribute every new megawatt to generative AI. There is another uncertainty. Forecasting data center consumption is extraordinarily difficult. A proposed facility is not constructed facility. A grid interconnection request is not necessarily a future customer developer's. Naomi, strike that. A grid interconnection request is not necessarily a future customer. Developers can submit overlapping plans, projects can disappear, technology can change, efficiency can improve, economics can collapse, and AI itself is changing so quickly that predicting how much computation will be required 5 years from now means predicting both technology and human behavior. Nobody can do that precisely, which creates two very different possibilities. In the first, today's forecasts underestimate what is coming. AI becomes cheaper. Cheaper intelligence creates more uses. More uses create more inference. Autonomous agents operate continuously. Robots begin using AI in the physical world. Scientific computing expands. Video generation becomes routine. AI enters medicine, engineering, logistics, education, manufacturing. Efficiency improves dramatically, but demand grows even faster. Economists have seen versions of this before. When something becomes cheaper to use, people sometimes use much more of it. Efficiency doesn't always reduce total consumption. Sometimes it unlocks demand, but there is another possibility. The AI investment boom overshoots. Companies build enormous computing campuses based on expectations of future demand. Models become radically more efficient. Specialized chips. Smaller models handle tasks that once required gigantic ones. Economic returns disappoint investors. Some proposed campuses are canceled. Some infrastructure becomes unutilized. The electricity system may therefore be facing one of the strangest planning problems in its history. Build too little, and you may constrain on the industrial revolution. Build too much, and consumers may inherit infrastructure constructed for demand that never arrived. That is the real argument, not whether AI uses electricity. We know it does. The argument is how much infrastructure society should build around an uncertain technological future. The grid starts to feel computation, and then the story gets stranger. A conventional data center can behave like a relatively stable electrical load. AI computing doesn't always behave that way. Training large models can involve thousands of specialized processors performing synchronized operations. Those coordinated computational cycles can create rapid fluctuations in electrical demand. In May of 2026, the Department of Energy Office of Electricity highlighted research into oscillations associated with large AI data centers. Think about what that means. Algorithms themselves can begin to have an electrical signature. A workload changes inside computers, and equipment miles away may need to respond. Computation becomes grid behavior. That's an extraordinary conceptual shift. For most people, an AI model exists as software. For an electrical engineer, however, that same model can become a changing load on a transmission system. Two people can therefore look at exactly the same AI system and see completely different things. One sees intelligence, the other sees megawatts, and both are correct. Texas hits the brakes. Then, on August 4th of 2026, Texas provided perhaps the clearest warning yet that the infrastructure question is becoming political. Governor Greg Abbott ordered a pause on approvals for the new data center projects requiring grid connections while the state conducts an audit. Why? According to reporting by Reuters, Texas regulators were confronting approximately 474 gigawatts of proposed new electricity demand. Around 90% of it was associated with data center projects. 474 gigawatts, that number should immediately trigger skepticism. It is vastly larger than Texas' existing peak electricity demand, which is exactly why it matters. Nobody should interpret 474 gigawatts as 474 gigawatts of inevitable future consumption. Many proposals may never materialize. Some may duplicate one another. But imagine being responsible for planning the Texas electricity system. Which projects are real? Which are speculative? How much transmission should you build? How much should we pay for? What happens if you underestimate demand? What happens if you overestimate demand? Suddenly, AI has created not merely an electricity problem, but an information problem for the electricity system itself. Grid planners need to know which future is real before they can build for it. And the future is being proposed faster than it can be verified. Who pays for the intelligence? This may be where the story becomes most human, because electricity infrastructure is not free. Someone pays for generation. Someone pays for transmission. Someone pays for substations, and someone pays for the grid reinforcement. Someone absorbs financial risk when projections are wrong. And that creates a deceptively simple question. If a technology company needs billions of dollars of new electrical infrastructure, should ordinary electricity customers help pay for it? The answer isn't obvious. Data centers can create construction activity. They can increase local tax revenue. They can support jobs. They can make utilities larger and potentially spread from fixed costs across more electricity sales. Dedication generation could even contribute electricity back to the grid under some arrangements. Supporters therefore argue that enormous new customers can help finance modernization the electricity system already needs. But critics see another possibility. Utilities invest billions to accommodate gigantic loads. Those costs enter the rate base. Electricity prices rise, and households and existing businesses end up subsidizing infrastructure created primarily for some of the wealthiest corporations in human history. There are already warning signs. Reuters reported in July that an Ohio manufacturer, Belden Brick, experienced roughly a 90% increase in electricity costs, driven primarily by rising capacity charges amid tightening regional power conditions. That single example does not establish that AI caused a nationwide increase in electricity prices. Electricity markets are far more complicated than that. Fuel prices matter. Transmission matters. Generation retirements matter. Weather matters. Regulation matters. Market design matters. But it reveals the distributional question hiding inside the AI boom. We talk consistently about who benefits from artificial intelligence. Perhaps we should also ask, who pays for the infrastructure that makes artificial intelligence possible? Water enters the story. Then another resource appears, water. Not every data center consumes enormous quantities of water. Cooling designs differ dramatically. Climate matters, technology matters. Some facilities use air cooling. Some use evaporative cooling. Some recycle water. And some companies are developing systems specifically intended to reduce water consumption. So statements like AI is draining our water are far too simplistic. But location changes everything. On the same day as the investigation, August 6, 2026, Reuters reported that Google's planned $15 billion data center project in Viskenhampton, India, was facing opposition over water and wildlife concerns. The surrounding region already faced water stress. Critics argue that guaranteeing water for a massive computing campus could collide with local human needs. The company says advanced cooling technology will reduce the project's environmental impact, while the government disputes claims that residential or rural drinking water supplies will be diverted. The dispute is unresolved, but notice what happened. A conversation that began with artificial intelligence became a conversation with water allocation. That is a signature of a system transition. Technologies become historically important when their consequences escape the category in which they began. The automobile began transportation. Then it became oil, roads, suburbs, urban planning, retail, war, pollution, culture, finance, real estate. The internet began as communications infrastructure. Then it began commerce, media, politics, dating, advertising, surveillance, identity. AI may be following the same pattern. It began as computation. Now it's becoming electricity, water, land, natural gas, nuclear power, industrial policy, and geopolitics. The environmental paradox. This produces another uncomfortable contradiction. AI is frequently presented as a tool that could help solve environmental problems. It may improve grid forecasting, optimize industrial systems, accelerate materials discovery, improve weather modeling, reduce waste, help design batteries, assist climate science, optimize energy use. Those possibilities are real. But the infrastructure required to operate AI can itself require enormous quantities of energy and materials. And where new electricity cannot arrive quickly enough from existing grids, developers may seek dedicated fossil fuel generation. That is already happening. So we encounter a paradox. AI may help optimize the energy transition while simultaneously increasing the urgency and difficulty of that transition. Both statements can be true. This is where binary arguments fail us. AI is neither inherently an environmental disaster nor inherently an environmental solution. Its impact depends on what electricity powers it, where facilities are located, how efficiently models operate, what cooling systems they use, whether workloads can move in time or geographically, whether AI produces enough useful economic activity to justify its resource consumption, and whether the infrastructure built for AI improves the broader energy system or simply competes with it. Could AI actually help the grid? There is another rabbit hole here that deserves much more attention. Data centers don't necessarily have to be passive consumers. Some computational work can potentially move. Not everything has happened exactly at the same moment. Certain workloads could be delayed when electricity is scarce. Computation could potentially move geographically towards regions with available electricity. On-site batteries could provide grid services. Backup generators could become emergency resources. Facilities could coordinate with utilities. The Electric Power Research Institute has documented experiments in which data centers shift or manage workloads in response to grid conditions. Google, for example, has demonstrated machine learning workload demand response with utilities. Now think about this reversal. We started with, how will the grid survive AI? But perhaps part of the future question can become, can AI infrastructure learn to behave like part of the grid? Instead of demanding electricity whenever it wants, a data center could theoretically become responsive. When renewable electricity is abundant, compute more. When the grid is stressed, reduce flexible workloads. When another region has excess electricity, move certain computation there. The batteries to smooth fluctuations, coordinate software with power markets. Suddenly the data center stops looking like a factory plugged into the grid. It starts looking like a programmable component of the grid itself. That possibility is real, but it comes with limitations. Not every workload can wait. Customers expect availability. Training schedules matter. Hardware utilization affects economics. Moving computation can create network constraint. And a company that has spent billions of dollars on accelerators generally wants those accelerators operating. Flexibility has value. Idle hardware has a cost. The technological possibility is therefore not the same thing as the economic reality. But this may become one of the defining engineering questions of the next decade. Maybe we're asking the wrong question. Return to that imaginary city, 10 gigawatts. At first, it sounded absurd. A city-sized electrical appetite devoted to computation. But after following the evidence, the number begins to look less like an isolated curiosity and more like a clue. Because perhaps we have misunderstood what artificial intelligence is becoming. For years, we measured AI by intelligence benchmarks. Now we can see the model reason. How can it code? How can it answer a question? How convincingly is its video? How quickly can it solve problems? Those measurements matter, but the next phase may require another set of measurements. How many megawatts? How much transmission? How many transformers? How much water? How many turbines? How much land? How much capital? How quickly can the generation be built? And the big one, who pays? In other words, perhaps the next AI benchmark isn't merely intelligence. Perhaps it's infrastructure. That doesn't mean electricity will permanently consume AI. History repeatedly demonstrates that engineers respond to constraints. Chips become more efficient, algorithms improve, cooling improves, networks improve, energy systems change, markets adapt. A constraint can become an innovation target. But that leads to an even deeper question. What happens if AI becomes dramatically more energy efficient? Does electricity demand fall? Maybe. Or does cheaper intelligence become so useful that civilization simply consumes vastly more of it? That is something we don't know. And it may determine whether today's enormous infrastructure plans eventually look visionary or excessive. There are at least three plausible paths from here. The first is infrastructure future. AI demand continues growing efficiently, improves, but usage grows faster. Gigawatt scale computing campuses become normal. Power generation and data centers increasingly develop together. Utilities expand transmission. Nuclear projects gain new customers. Natural gas generation grows where speed matters. Renewables and storage expand where economics favor them. Computing becomes a major permanent category of industrial electricity consumption. In that world, today's announcements are not excess. They are beginning. The second is the efficiency future. Models become dramatically cheaper to operate. Smaller specialized systems perform jobs that once required giant frontier models. New chips deliver much more computation per watt. Training becomes more efficient. Inference costs collapse. Data center demand still grows, but much more slowly than today's aggressive projections. Some proposed infrastructure never gets built. In that world, the constraint forces innovation. And then there is disruption future. The economics of AI disappoint. Or a new computing architecture changes the equation. Or regulators impose new infrastructure cost. Or local opposition delays projects. Or supply chains cannot produce enough turbines, transformers, and electrical equipment, or electricity prices make certain forms of brute force scaling economically irrational. In that world, today's race for gigawatts becomes a lesson about exploration technological booms. We cannot currently know which future wins, and anyone who claims certainty deserves scrutiny. But we can watch the evidence. Actual data center construction, actual electricity consumption, actual model efficiency, actual utility investment, actual power prices, actual generation additions, actual cancellations. Not announcements, not hype, not fear, evidence. The real machine. Now return one final time to that first image. 10 gigawatts, a data center beside its own energy system. At the beginning, it looked like an extraordinary project. Now it looks like something else, a possible prototype. Because perhaps machine we are building isn't artificial intelligence model. Maybe the model is only one component. The real machine stretches much farther. From a semiconductor fabrication plant, to a GPU, to a server rack, to a cooling system, to a substation, to a transmission line, to a gas field, a nuclear reactor, a solar farm, a battery, a reservoir, a community, a utility bill, and eventually to the question you type into the screen. The intelligence may be artificial. The infrastructure is very real. And that may be the most important thing that AI revolution is teaching us right now. There is no cloud. There are only other people's computers. And behind those computers, there is an electrical system. Behind that electrical system, there are physical resources. And behind those resources, there are choices. Who gets them? Who pays for them? Who benefits? Who bears the risk? What should we build? And how much of our physical world are we willing to reorganize around the possibility of machine intelligence? Those questions can't be answered by an AI. They cannot be answered by a technology company. And they cannot be answered by fear. They require evidence. So what evidence should change your thinking? If AI becomes 10 times more efficient, would that solve the energy problem? Or make AI cheap enough that we use 100 times more of it? Should technology companies be required to finance the generation and transmission infrastructure their facilities require? Should communities have greater authority over how electricity and water are allocated? Could flexible computing actually strengthen the grid? And 20 years from now, when historians look back at the enormous data centers being proposed today, will they see the infrastructure that powered a new industrial revolution? Or monuments to one of history's greatest investment bubbles? We don't know. Not yet. And that's precisely why this rabbit hole matters. If today's episode made you think, don't stop here. Read the research, study history, examine the original documents, listen to experts, listen to the critics, listen to people who disagree with you, question the strike that. Listen to the people who disagree with you. Question the sensational claims. Question the official explanations. Question the headlines. Question the experts. Question your assumptions and question mine. Because Rabbit Holes Deep Dives is not about handing you a conclusion. It's about following the evidence, even when the evidence leads somewhere uncomfortable. What evidence changed your thinking? Which claim deserves more investigation? What did we miss? Which assumption should we challenge next? In what rabbit hole should we go down next? Share this episode with someone willing to examine the evidence. Join the conversation. Challenge the ideas respectfully. Keep asking questions, because every answer opens another question, and every question leads us farther down the rabbit hole. Put your comments below. I read every one. My name is Leroy Nellis, and this is Resilience Radio. Godspeed. stand for the Constitution, and never surrender your ability to think for yourself. God bless and good night. Hey, everybody. I wanted to sit down with you today and talk about something we've been working on behind the scenes for quite a while now. First, I want to thank you. Whether you've been here from the beginning or you just found the channel recently, I want you to know that I genuinely appreciate every single one of you. Every comment, every conversation, every suggestion, every word of encouragement has helped shape what Resilience Radio is becoming. This isn't just my channel anymore. It's about a community. And because of that, I wanted you to hear these changes directly from me. Over the last several months, we've been doing something a little unusual. We've been studying our analytics almost obsessively. Not just YouTube analytics, but the analytics coming from Naomi, the AI production system we've been building from the ground up. We've been asking questions like, what videos do people come here for? What keeps people watching? What topics naturally fit together? And what happens when we mix very little types of content on the same channel? After looking at thousands of data points, we came to one conclusion. It's time to let each series become a very best version of itself. So today, I'm excited to announce that Rabbit Holes is becoming its own dedicated YouTube channel. Rabbit Holes deserves its own home. It's where we dive into mysteries, history, unsolved questions, and rabbit holes. Strange events, forgotten stories, and all of those fascinating topics that make us lose track of time. By giving Rabbit Holes its own channel, YouTube can better understand who those videos are for. Our AI can learn from much cleaner data, and we can build something truly special for people who love those deep dives. Resilience Radio will continue doing what it has always meant to do: help people understand themselves through psychology.
You pushed me down, thought I'd stay on the ground, counting me out like the numbers didn't matter. But pressure builds diamonds in the dark, and I've been sharpening my edge in the chatter. Every scar turned into strategy, every setback fueled my clarity. I took the hits, learned the game, turned my losses into flame. Now I'm coming back strong, and you'll remember my name. I'm rising through the fire, breaking every wall you built around me. Heart's a battle drum,